Let's do this. Cool. Brad, would you like to take it from here?
Sure. Right. Can everyone hear me? I'm going to take that as a yes. Okay. So starting off. Right. So we're going to discuss, I think, three different areas: medical data, medical machine learning, and then how generative adversarial networks can work with both of those. As a bit of background, I'm Brad. I'm a sixth-year medical student, and I've also just finished my MSc in electrical engineering, working on applying GANs to medical imaging. But I think they honestly have quite a few applications beyond just that. So as a first, there's a bit of a primer on medical data, because I think it ends up being lumped as something of a simplistic idea, and it actually ends up being very complicated the second you start delving into what it actually is. Now, generally, medical data is any of the data we collect in the clinical practice and the care of patients. And I mean, I was surprised to learn that it actually is considered to be one of, if not the largest source of global data. They estimate that around 30% of all global digital storage is devoted purely to healthcare data. And I mean, they say that the typical patient in a digital health system accrues around 80 megabytes of medical data per year. Most of that is imaging data. So some patients actually end up accruing gigabytes of data in a year because of the imaging component. But it is a field that is currently growing. They estimate that 45% of these healthcare sector of institutions currently responsible for hosting healthcare data are going to be significantly upscaling in the coming years. And so realistically, it is a truly massive entity. Now, the problem is actually pinning down what constitutes medical data is a very, very, very context-specific question. And it's not just a question of the kind of healthcare environment you're in, of whether you're in America or if you're in the African region. It's also a question of the medical specialty you're working in, the healthcare sector you're interested in, and even perhaps the kind of patient that you're involved with. And I mean, I put together one particular model that they have for the kind of data that you may be working with. And it's everything from imaging to time series signal data to some kind of textual representation. But the exact proportion and scale of each kind of data will depend on the kind of patient you are, the institution you're in, and the resources you have access to. Also, the exact goal of that data is often strongly dependent on the reason it was collected. Is it for a long-term follow-up or for monitoring of patients' performance, or is it for more of a diagnose and solve the problem right now kind of problem? And all of those biases tend to come out in the data that we're going to be discussing. So the next issue is, what are the issues with getting this data? Because obviously, if it is the biggest set of data that we have globally, why is it not everywhere? And this slide sort of reads almost like the components of the entire healthcare sector, but the reality is that there are problems at every single level. And they start at the very highest point because healthcare data is incredibly protected. I mean, most countries, especially as they become more digital, have large overarching laws that protect the dissemination of personal information and put requirements on how healthcare information has to be stored or disclosed. There's also, even if you can perfectly anonymize this data or you have the ability to share it, the problem tends to be that people are quite unwilling to share it. It's often housed in academic or healthcare institutions that intend to use the data for their own research or to benefit themselves or their own patients. And so there's oftentimes difficulty in getting people to share. Additionally, not in terms of just getting access to the data itself has problems. And I'm not necessarily speaking about what I have there as the data point on this, where we're talking about errors in data collection or actual problems with the data itself. The problem I'm trying to get at here is that oftentimes the pathophysiological processes we're interested in, the patients we're interested in, those processes are heavily biased. Diseases are biased to specific parts of the population, and there's always an argument and discussion about how parts of medicine or the practice of it may in fact be biased. And so that also may be coming out in the data. Additionally, the actual process by which we are collecting this data may be biased or may leak important information that can distract from whatever predictive goal we are trying to get at, which we'll discuss in a little bit. So from all these issues, we generally have this overarching problem that we have this ethical goal to try do what is best for the patients we serve, or try to build the best tools for them. But oftentimes we can't do such because we can't get the data that is necessary to build these kind of tools, or to attempt to solve these problems. And there are a few focal issues that come out from this in medical machine learning. Possibly the most significant is that when you are looking at training data for building these kind of models, there is a absolute gluttony of normal studies, with the majority of imaging studies being performed, or any kind of, if you think at ECGs, if you're looking at physical examination notes, the vast majority of them are completely normal with barely any abnormalities. And the cases that have abnormalities are always going to be a minority. This is a problem that is worsened as you try to specifically segment classes. So the example I always come back to is chest x-rays, because they're my absolute favorite. But the example is this, is that if you have 85% of your scans being normal and the residual 15% having pathology, those are obviously not going to be equally distributed between the kind of diseases that exist. And you have two problems there. The first is that those are going to have their own individual incidences, and they're going to be imbalanced. But the problem is that patients are allowed to collect as many diseases as they like, and oftentimes they are not limited to have just one at a time. And so the idea of class intersectionality becomes a problem for this kind of data, because if a patient has TB and they have cancer, the chest x-ray findings for that are not going to resemble some kind of composition of both. They're going to be altering it in a way that creates almost a new class entity. And so the problem is that even if you have sufficient data of individual class examples in isolated cases, you will always have a deficiency of the intersection of classes, where the model will perform poorly when you're trying to work on examples where you're trying to look at combinations of conditions, or where a patient may have had a previous condition that's resolved and sitting on a new condition. Beyond that, there's always this concern about having diverse data, both in terms of what we've discussed already about having classes, but also about the kinds of patients and the kinds of collection methodology that you're using. And we'll discuss more about that in a second. Because that also leads into a whole discussion of bias, which is that the oftentimes, if we look at the data that we're collecting, if we're already saying that there's biases that exist there may be biases in the way that we have already collected the data, there may be biases in the way that we are processing it, and generalizing that to a model that we're going to implement is going to be a significant problem, in that we can completely globalize or systematize completely unknown biases. So as an example of where this process of data diversity becomes important is this paper that came out last year. It's a bit of a discussion on how, if you just collect the 3 largest chest x-ray repositories currently available on the internet, and I mean, the main issue with them is that they are collected from single institutions or a set of institutions from healthcare institutions from a single university, and oftentimes serve a single geographical area. But because they are the ones that have been made public and distributed, they are often the benchmarks through which we develop models or evaluate models. And the problem here is that they've shown that the actual rate at which we detect diseases between in the different images within these data sets differs based on protected characteristics, such as the patient's age, such as the patient's sex, ethnicity, or even their medical aid that they have, which they use as a proxy for the socioeconomic class of the patient. And I mean, there is always a debate to be had that there may be differences in diagnostic difficulty, or there may be other features there that can potentially give rise to these differences. But some of them don't necessarily lend themselves to easy explanation, even once you control for differences in prevalence, or if you look at conditions which shouldn't have any kind of realistic difference in diagnostic difficulty. And so it becomes important to attempt to balance your data sets, because what they found here is that by having data sets that are well balanced and distributed across multiple different sites with quite a high level of diversity, these differences between protected characteristics tend to dissipate, while the actual diagnostic difficulty or the differences in methodology in scanning the patients don't tend to change. So it seems that one solution they have for resolving all of these problems is to have more diverse data. The other discussion here is that it becomes important to look potentially at these protected characteristics, because as an example, this paper came out just 2 months ago, and it demonstrates that to an almost shocking degree in both chest x-rays, CT scans, and ultrasounds, machine learning models can pick out a patient's race more easily than it can almost any other diagnosis at incredibly limited resolutions, even with highly degraded images. And it does so in a way that the radiology literature has absolutely no understanding of how it is doing it. And so any kind of imbalance or bias that is going to be clustered along sex or race, these models are capable of pulling that out. So the question is, how can we potentially resolve these kind of disparities? And there are generally two paradigms oftentimes working in tandem. The one is, how can we do it at a training level? And I mean, the easiest solution to this is to attempt to augment our data in training, which is, you can think of it as potentially just making more data, but the reality is you can selectively augment specific classes to try give greater diversity to classes that may not have as many examples. Perhaps the most painful method is attempting to resample your data sets so that you can have, you can either discard your oversampled classes or attempt to duplicate examples from undersampled classes. Oftentimes, the simplest solution is just to weight your cost function. And what this can mean is you can either look at the incidence of disease and inversely weight it so that your model is given a very high cost for errors in very rare diseases. Or another way of thinking about this is you can potentially look at the protected characteristics of patients and penalize models for having differences in performance between different patient sexes or patient ethnicities, so that you get an equivalent error rate between all groups. Perhaps the more effective solution, though, is usually just to have more data and to have more diverse data. The potential conventional solution that we currently use is the removal of patient-specific information. And I mean, the most popular example of this at the moment is your MIMIC data sets. This is both an electronic healthcare record system and an imaging repository. And the way that they have been able to publish sort of the entire data bank of a hospital over several years is they have had to go through several loopholes to scramble a lot of patient-specific information. And one of the main ones they use is time scrambling. So they move the patient's timelines around so that a patient will be admitted in 2072 and another one will be discharged in 1930. And so the internal time differences between events for a single patient will be consistent, but you can't tell which patient arrived at the hospital in what order. there's also harsh limitations that are put on due to legal restrictions. So age cutoffs and rare condition removal is one example. Any patient over a specific age has to be removed from the data set because they're considered to be rare enough that you could potentially identify them based on just their clinical characteristics. The same with rare diagnosis. The image version of this uses optical character recognition to read markup on the images. And I mean, this is, of course, in addition to metadata removal, but this is going to remove any kind of text markup on the image that could potentially have a patient's name or a location that could give away who it belongs to. Another solution here is the idea that Archie's previously spoke about, which is federated learning. Definitely give her talk a listen on that. The last idea, and the thing that has benefits beyond simply just producing more data, which we'll discuss in a little bit, is that of data generation. And there are a few different ways of going about this. And one specific way that I was asked about in an email was about simulating synthetic patients using explicit modeling, which is there's a product that does this called Cynthia. And the other method is doing it implicitly through generative adversarial networks. So before we get on to the discussion of GANs, what is Cynthia? Now, Cynthia is a method of producing a full electronic health record of patients. And it does so by explicitly modeling all the different ways that a patient may present to a hospital or the kind of data points that they may get. It does this by explicitly designing all the different kinds of disease entities that a patient may have. So this is the example for food allergies, but there's another one for anemia, another one for leukemia. There's quite a few different modules that you can use. And I mean, the question I was asked was if this has applicability to use of for generating data for patients in Africa. And I mean, I think the big problem with this kind of modeling system is that, firstly, you have to define every single explicit step in a way that it's often very difficult to figure out what those probabilities are going to be. And I mean, they derive it a lot from census data, but that's not going to be readily usable outside of the immediate population that they've looked at. And beyond that, it requires you to have a completely perfect understanding of the ways patients present, the mechanisms by which the diseases progress. So it ends up being an incredibly difficult entity. And most importantly, you don't necessarily understand how these conditions may interact with one another. So it ends up becoming incredibly difficult to model. And so as far as I understand, the main utilization of this tool is for generating data sets that you can use for validating IT solutions or for testing new modules for IT interfaces without actually using them for real patients. GANs, on the other hand, can be used in a different manner because they can produce, without explicitly modeling any of these interactions, data that is statistically completely identical to the source distribution. So firstly, let's have a bit of a discussion of what is a GAN. So it's now a 7-year-old technique, and the basis of this is fairly simple. You've got two neural networks, a generator and a discriminator. The generator samples from some random distribution and is tasked with modeling a synthetic sample from that random noise, and it feeds that to a discriminator. The discriminator will take in a real sample alongside the synthetic sample, and its job is then to decide which is real, which is synthetic. And the training signal is provided to the generator about how adequately this synthetic sample was able to fool the discriminator, and to the discriminator by how effectively it was able to separate out the two distributions. This progresses through training to the point where it will reach an equilibrium point once the synthetic samples produced by a generator are indistinguishable from real samples, and the discriminator is forced to just guess 50% probabilities of either one being real or synthetic. Now, whilst in theory, the problem has largely been training stability with getting these systems to work in practice. oftentimes, as the resolution goes up, or as the data becomes increasingly, if we work on tabular data, as you get more and more covariates, the problem becomes that the higher dimension you have, the easier it is for the discriminator to identify synthetic variants. So we've come a long way since the initial model in 2014. And so we can reliably now train quite large generator discriminator pairs. It's just oftentimes quite expensive computationally to get these full systems working. So here's an example of what a GAN looks like. This is one I put together for building very, very small chest X-rays. This is a deep convolutional GAN, and you can see the generator progress from initially generating completely random noise to things that look increasingly like chest X-rays. Importantly, if you are looking in this example, the generator never has access directly to looking at what real samples look like. So it can't copy the distribution. It simply knows what features, or it learns what features must be produced in order to maximize the discriminator's view that it's a real image. And so it learns feature combinations, but not individual images. Importantly as well, there's not a one-to-one relationship between synthetic and real images. And so you can't identify necessarily what image was used to produce what generate. So as examples of what GANs can be used for in general practice, this is the images used from StyleGAN 2. They're for megapixel resolution face image generation. They come across as incredibly realistic and are oftentimes very difficult to discern from images of real people. That is trained in an unsupervised fashion. So same as the original GAN formulation, you simply just give a distribution of images and ask it to produce a clone of that. More convoluted setups of GANs are possible. This is an example of Segal GAN, which attempts to conditionally change the content of an image between two sources. You oftentimes see this if you are looking at photos that have been translated from one style to another, or semantically modifying things like pictures of horses to pictures of zebras and vice versa. A variant of this is this pix-to-pix architecture for image-to-image translation. It will take something like this, which will be a reference image that you'll ask to convert to something resembling a building, and it can actually produce something that resembles, it's modeled from your input image and looks realistic. Obviously, deepfakes are an example of this technology being applied to video, and ultimately, you can use GANs for a lot of these poorly defined tasks of wanting to produce high resolution, high quality images or videos from, or even tabular data from specific conditional source information. The problem when applying this to medical data is that oftentimes, as we mentioned before, they are multi-class or multimodal. And the issue is that when trying to define how to generate those interactions, you firstly may have an incompletely labeled image. And so you may have labeled 14 conditions that could appear on an X-ray, or you may have only a certain number of covariates labeled in a table. And you may need sufficiently more to properly describe the level of variability that may be present in that image. And so it's actually an evolving problem now to attempt to resolve this generation of multi-label data. There's quite some interesting stuff coming about it, and I'll show you one example I worked on in trying to generate that kind of data. But generally, if we look at the ways that you can apply GANs to medical data, there's generally an ABC sort of approach where you can use it for augmenting data that you already have, for producing new data to balance out your data sets, or, and I think potentially the more interesting variant now is fully cloning a data set to produce a statistically indecipherable duplicate that has the same outcomes, but has none of the concerns of patient privacy or patient identification. So This is an example from my recent project where we worked on generating megapixel resolution chest X-rays. And it's the PG GAN there stands for progressively growing GAN. The idea behind this is you produce progressively greater resolution images so that it stabilizes training. You're not trying to straight out generate high resolution images. And I mean, all these are examples of chest X-rays that are produced without any form of conditioning. It will produce it just at random. The benefit is then you don't have to try specify the specific disease that should be present in the image during training. It generally makes training incredibly difficult and oftentimes very challenging to get it to produce specific disease entities straight off the bat using that kind of methodology. So these are the chest X-rays produced at a megapixel resolution. Here is an example of how that process works. It will start off by generating a 4x4 pixel grid. Once that's stable, it'll move up to 8x8, eventually to 64x64, and eventually at a megapixel. Now, how can you augment images? This is one of the more interesting methods, I think. So let's say this is your chest X-ray that you have as you have it from your source data set, and you've trained a GAN now for producing similar kinds of chest X-rays as your source. You've potentially thrown in a whole bunch of diverse chest X-rays that you didn't have labeled before, but the system can learn to produce similar looking X-rays because it's unsupervised, so you don't need labels to do that. And now you want to produce images that can provide more examples of a particular class or to diversify the images that you want. Now, let's say that you don't have class labels, you want to do that. So in this example, you can minimize the difference between a generated image and a reference image that you want. And so you can find an example in the latent space. So you find in this point that this image very closely approximates the image that you have, and it appears diagnostically similar. You can then sample in a radius around that image for images that will have incredibly similar features, but differ semantically in ways that you wouldn't be able to achieve just by randomly rotating, flipping, or changing the color gradients of the image. So here's just 3 examples where the image is very largely similar, but the text markup differs per the image. Things like the contrast changes, positions change very, very slightly, but overall, the actual content of the image is remarkably similar. And you can say that the labels for these images would be largely similar to one another. You can do this with tons of images from your data set, and you can massively diversify your images. If your GAN was trained on images also that were not included in your source data set, it may vary in ways that weren't present in the original data set, which could improve robustness to out of distribution errors, or may simply just improve your test accuracy. Looking at alternative methods, you can also use examples from the cycle GAN methodology, where you can have translation between images with tumors and without tumors to produce examples of various different pathology entities. So you could add tumors to previously healthy tissue for tumor classification models, and use the difference between your produced images and the source images to add bounding boxes, or even segment the differences as potential additional training data. This also works in this example where they've changed the kind of weighting that was used for an MRI. So if you have additional data that is done in a different kind of weighting or in a different format, you may be able to even use it in a different kind of model by changing the color palette that's being used. In terms of class balancing, this has previously been quite a significant problem with using GANs. This is an example from 2019 where using DC GANs, they were able to balance out a chest X-ray data set for classification purposes. Now, you can see here that in terms of distribution, these are the additional sampled images that they had to add in order to fully balance out the data set. Now, the problem with this is twofold, which is that as your GANs get better and better at synthesizing realistically looking images, the cost of producing those models goes up tremendously. It requires significantly more computation. These images produced here are produced using a DC GAN architecture, which can be trained in a couple of hours or even dependent on resources, maybe just an hour. But training a high resolution GAN to produce megapixel images takes days and oftentimes requires quite sophisticated computer hardware in order to even make that time tractable. So the issue here is that in order to balance the data sets, they had to train an individual GAN for each class of the data set, because in order to stably produce an example of each class, given the multi-label setup, they trained a single classifier just for each condition and generated images as an example for each condition. The problem is that the second if they were to try to do that at greater resolutions, you'd be looking at several weeks of training to cover the 14 different classes that exist in this data set. So it's not really a tractable solution for balancing data sets. One of the solutions that has come out, and this is something I worked on, which is that if you take an unsupervised GAN and you just freeze the generator, you can perform a search through the latent sampling space for examples of a class if you've got a classifier for that disease. And this is an example what you can do. So you can take a generator that has no specific way of controlling the kind of disease that it produces, make it produce a random chest X-ray, and then force it to maximize a specific class in your classifier. And it will search for a specific image that meets that criteria. You can then tune how severe you want it by introducing the threshold by which you'll consider things positive, and by that method produce examples of different classes, despite the underlying architecture not being able to produce classes at all. You can see here that it produces examples of most of the various different entities found inside the chest X-ray 14 dataset. What's quite interesting is that because you are working in a multimodal setup now, you actually preserve your pathology interaction. And this is something I found very interesting. It was, if you produce cardiomegaly examples, now, as you increase that threshold, generally the severity or the how obvious that pathology is becomes more apparent in the image. And what generally happens is, as that becomes significantly higher, you start collecting the interaction that condition will have with comorbid conditions. So patients with severe cardiomegalies will start presenting with features of heart failure. So they'll have pleural effusions, or they'll have pulmonary edema that you can start seeing will become apparent with higher levels of cardiomegaly class scores. So you can actually see that the generator model naturally pairs known comorbidities that are related with like a pathophysiological interaction to the underlying conditions when they start when they start generating them. Similarly, when you generate mass features, there's another label for nodules for lymph nodes, and that also generally becomes positive when masses become positive, which is something else which you'd expect due to the actual pathophysiology of how that process will work. What's quite interesting, I think, from this is it lets you generate specific classes to balance out your data set, but it doesn't necessarily have to be a classifier from that data set, because your GAN is going to be a fixed image generator, and it can only produce images that it's trained to mimic. And so if you have trained it on a image data set from a different institution and you're trying to maximize images that have mass labels or have fibrosis, it should largely resemble the images from that data set, even if those conditions weren't labeled in that distribution. That sort of brings us on to this whole idea of fully data sets cloning using GANs. And I mean, this is something that's been attempted both with tabular data, signal data, and imaging data. And what's really interesting is that you can just add additional cost functions to the GAN formulation to just ensure that the generated data sets actually maintain the same statistical properties as your source data set. Given that we've already mentioned there's no one-to-one relationship between samples, you can't readily identify which sample came from where. They've even in these specific papers analyzed how difficult it would be to identify which patients contributed to a particular record or if they were included in a data set. And they found, I mean, the general conclusion from these is that it's incredibly hard to do. Additionally, you can then have this idea that you can potentially share completely protected data sets with perhaps rare conditions, and the ensuing data set that you've released can be analyzed in the same way as the original, produce similar or even the same statistical conclusions or the same models, despite the fact that the information you've shared doesn't violate any patient's privacy or doesn't have any risk to the patients that have been included. The example they give here is generating fake tables and then building machine learning models using both tables and comparing them, and they generally have near identical performance between the two. Doing this with the images is a bit harder given the discussion we already had about trying to perform multimodal sampling, but using that methodology and this technique, you can actually get quite close to the way there in terms of performance. So the way to read this table is these are the diseases, and this is per class RSC scores. And how it works is the model will be trained only on GAN generated labels and images and evaluated on real images. And so these will all be evaluated based on the same set of real images. And so you can see that if trained on real images and evaluated on real images, it does incredibly well. But you can actually get quite a significant way there when training on images that are produced purely from searching through the GAN latent space and then just attributing the label to what the classifier was optimized for. And there's reason to believe that this performance difference isn't due to limitations in the technique, but rather just limitations in the quality of images being produced from the GAN architecture, because there are quite a bit more powerful architectures than PGGAN now. And the reality is that it's very likely that the score difference will continue to drop with the use of better GAN models. This, as an idea, means that you can potentially rebuild the training data necessary to construct the classifier without having to release any of your original data set. So similarly to the table model, being able to create a fully public data set that no matter how unique the conditions, or no matter how specialized the use case, it's possible that no one in that data set would be readily re-identifiable. So I think that the benefits of this mean that you could potentially have not only greater access to shared data, but it means that you can potentially remix data sets in ways that wouldn't be possible even with techniques like federated learning, or just simply combining them into one set that you then try train off, because there is the possibility of attempting to create data labels using this technique from a data set that never had those labels in the first place, using the GAN as a method of labeling that data by generating class examples. And I think the ways forward on this is that there needs work to be done in two ways. The first is for the tabular data. The problem at the moment is if you look at Cynthia, the way it explicitly models patients and generates them is that it has this wonderful longitudinal process to it, because it explicitly produces patients over the entire lifespan and interaction with the clinical environment. And you don't really have that kind of constraint with these table GANs. And so I think the next phase that is going to be necessary to make those interoperable is being able to have these nice long-term dependencies, which should enable them to learn these massive interactions in the relational data tables that you have in electronic health records to produce ideal reconstructions of that. The one example where they attempted to do that, which is this previous paper here, the generating multi-label patient records, they used LSTM GANs to attempt to produce long-term coding for patients in terms of ICD coding, and it worked fairly well. So I think that needs to be expanded to more diverse data, not just the ICD coding. And for imaging, there's more control necessary over the exact individual patient characteristics that will be necessary for it to be readily useful. And I mean, when that starts becoming useful, you can do incredibly interesting things, like if you were to generate, if you were to potentially use something like the style GAN architecture, which has quite fine-grained control over low-level image details, you may be able to do things like generate lines, or you may be able to generate, so the one example is endotracheal tubes or intravenous lines, and then differ that against the original source image and use that to train something like a segmentation model for identifying those in images. So I think there's quite a lot that has been done in progress in this domain. There's definitely a long way to go to making it readily usable for every use case, but it's definitely a way of looking at bolstering the data that you have access to by making it possible to remix or combine data sets in semantically interesting ways. And it's a way of potentially squeezing out just that little extra bit of performance by being able to cut into that class intersectionality problem and into the normal versus abnormal ratio imbalance. And with that, that's everything I have to say on that. So if anyone has any questions or anything you'd like clarity on, the floors are yours.
Cool. Thank you, Brad. That was a superb talk. I really appreciate that. You're doing some really interesting work. You've described your research to me before, but I have a new appreciation for it now. So just before we jump into questions, because I definitely have some questions of my own, because in this community we try and speak to both people with machine learning backgrounds and from the quantitative side, as well as people with healthcare backgrounds. So, in terms of how we address the questions further, I'd just like to quickly, by a show of hands, and you can do this with the reactions button, like at the bottom of your screen in Zoom. Those of you here who have healthcare backgrounds, could you raise a hand quick? All right, perfect. And then those of us here who have a machine learning background, you can also raise a hand. I'm just going to keep my hand raised because I think there are some of us who are the intersection of both. Okay, cool. Right. So yeah, with that information, let's continue ahead. There are some questions in the chat. I'm going to ask just one question quickly. I'm going to go through the questions in the chat. I'm going to open questions to the floor, and then I'm going to circle back with some questions of my own. So my first question, Brad, I'm just really eager to know, those results that you showed in your performance slide, are those from your own experiments?
Yeah, so that was from the paper put out on generating synthetic chest X-rays.
Awesome. That is some really, really cool stuff. Cool. So where was that paper published?
It
Or
was
has been
in
published?
Spring. Yeah, it was published with Springer Nature Computer Science
When was that?
in June.
Oh, nice, dude. Very nice. I wasn't aware of that. You got published. Good job.
Thank you.
Cool. So let's let's go through some of the questions in the chat. We'll start with Tabung. You're welcome to ask your question yourself, or if you like, I can ask the question for you. I'll give you an opportunity to unmute your mic. Go ahead.
Hello. Thanks for the talk. I just want to ask, so yeah, I have a few questions. Sorry about that. So you said GANs can sometimes, I think not GANs, like machine learning can sometimes do so good in medical data, especially x-rays and stuff, right? Without any understanding. So, you know, everyone can do, I mean, most of us can just write code that can do really good things, but then as soon as you give to the expert, they, you know, you can't explain how the results were obtained. Like, what do you suggest? Do you have any solution that you think, you know, how do I explain that to an expert? And then the second one is, what measure did you use to measure the similarity of the original and the synthesized, both on your X-ray data set? And I had another question. Oh yes, so okay, that's fine for now. Sorry, it's fine for me.
Sure. So let's go with that in reverse order. So for similarity, we did a few things. So the first is generally for GANs, current standard is to use the Frechet inception distance, which looks at the distance between the average set of images embedded within an inception V3 model. The problem with that as a technique for this is that obviously the inception model has been trained on ImageNet or similar, and doesn't have any biomedical imaging in. So we actually had to validate that you could use the FID metric for evaluating the similarity between synthetic and generated images based on X-rays, because I mean, before, if you're using it for human faces, it's possible because there's images of humans in the data set that network is trained on. So I mean, what we had to do is we had to actually split chest X-rays by class and calculate FIDs between individual classes of a chest X-ray, and demonstrate that the distances calculated actually correlate not only to the degree of distortion that the disease pathology would have on that specific condition, but that the distances actually clustered similar disease patterns together. So that was the one method. The other was expert review. So we had some radiologists look at samples of, it was clusters of mixed random real and fake x-rays. They had to pick out the real x-rays. They had then pairs of images they had to pick out. And we also attempted to get them to provide diagnoses for some of the generated images. Just some points on that. The main issue we had was the radiologists actually were very good at picking out some of the synthetic images. A lot of them noted that some of the bony details when you zoom in don't exactly mimic what you'd expect to see on a real X-ray. And that some of the shadowing that you'd expect isn't as crisp as you'd expect on a, crisp is probably not the right word, but it's not as, it's different to how real images present that information. And so they were actually quite good at picking it out. interesting that their actual score in terms of the rate at picking out fake images is similar to that of the PGGAN in other tasks. So there is some expectation that using newer GAN setups or different GAN setups may improve that metric as well. So that's on similarity. In terms of explaining to an expert, that's an excellent question. I have to admit, it's something that, I mean, I've been reading a ton about it, and it's such a big issue because increasingly, and I think one of the excellent examples is that reading racial identities from X-rays and CT scans paper, because the techniques we've developed for that now, things like GANs or things like saliency maps to attempt to show pixel based importance for diagnostic tasks. And I mean, for the racial identity paper, it's really worth an excellent read. I'll just go back to it so you can see it. The reason I found it really impressive is it is so comprehensive in how they evaluate this problem. They externally validate it. They look at multiple different data sets. They look at almost every kind of human-based pathology, like mechanism they can try to explain it. And what they conclude at the end is that the saliency maps, which are very, very popular, absolutely do not explain this relationship in a way that we can understand. That knowledge of differences between ethnicities in terms of adiposity disposition, or in terms of disease entities, or in terms of like any kind of known incidence difference between groups, doesn't explain how effective this system is. And so I think the problem at the moment is explaining to an expert is really an open question. We can, for some of these problems, we can give a good idea, because sometimes GANs actually do correlate well to the areas in which you look at, but they don't necessarily work well with the underlying pathophysiology, because they don't have access to that information. So I mean, my honest opinion on it at the moment is that these tools are not at a point yet where we can use it as a stand-in replacement. I think we're at a point where you can use it for triage, you can use it for decision support, but it's not the kind of tool that you can just swap it out and replace, because the explainability is just not there yet. I hope that answers the question.
Thank you.
Sure. Are there any other questions? Please just feel free to unmute your mic and fire away. Otherwise, if you don't feel like talking, you're more than welcome to put a question through in the chat, and then I'll ask it for you. So I'm just going to provide a moment for anyone who would like to ask a question to unmute their mic. Okay, cool. I take that as there are no more questions from the floor, I guess, for now. Oh, Trio, would you like to ask a question?
Yeah, hi guys. So I was wondering, are the scales for males and females, are they the same or are they different? Thank you.
So can you clarify what you mean by, did you say scales?
I mean scans, like
oh, scans.
Yeah.
So broadly speaking, they're the same in terms of the way the scan is done. But like, for example, on a chest X-ray, there's a known problem where depending on breast size, for example, you can see breasts on a chest X-ray. And there's a potential, for example, diagnosing nipples as nodules in the lungs. So you expect a higher false positive rate in females, because that is a diagnostic error that is made by humans and may even be present in some of the label data. But it's going to be very, very, very dependent on the condition you're talking about and how that influences. Because as an example, how these things can intersect. I've seen a chest X-ray of a woman who had heart failure and breast cancer. Now, generally, you would see pleural effusions on that chest X-ray, but she's got a very large mass in the breast that obscures that. And so she has pleural effusions. You just can't see that on the image due to the other, the mass obscuring that. That is something that's statistically significantly more common in females and makes that diagnosis much harder. So it's just the way that the scans may differ, not based on like the fact that the scan is different, but the actual diseases that are possible or the interactions that are possible are very dependent on the patients that you have and the diseases that are present. Does that answer the question?
Yeah, I just wanted to get that one.
Cool, thanks for that question. Are there any more questions? Again, I'll just provide a moment for anyone to unmute their mic. Cool, no more questions that I see. I've got one or two questions for you, Brad. So just to try and understand a little bit more could I ask you to maybe share your screen again and then go back to the slide where you have the generator that's been fixed, the generator network that's been fixed in the classifier. I guess just as a reference point.
Sure, just give me 1 second.
Sure. And then once you're there, I'll ask a question around that. I don't know, sometimes I feel it helps to have something to look at when talking about these things. Sorry,
Right, can you see it now?
Yes, sorry for the added effort there.
No stress. Right, so you wanted the fixed generator. Yeah, no. This one.
Yes. So the way I understood you explaining this is you train that generator as you would a normal GAN, and then you're essentially, I'm not going to say fine tuning it on the classifier. I'm going to say you're trying to take those learned latent space representations and then disentangle them. So you've got this entangled representation in the generator that has all of those conditions on the right, and then you're using externally trained classifiers to tease out a representation for cardiomegaly, or a representation for pleural effusion, or a representation for emphysema. So what I understand you're doing is you're disentangling those representations. Is that a correct interpretation of that?
Yeah, so that's definitely one way you can think about it.
Okay.
I will say though that these may have one label here, but oftentimes they'll have multiple representations. So this is just the class that has been optimized. So oftentimes cardiomegaly will have maybe one or two other labels as well, because it'll be cardiomegaly and pleural effusion and pulmonary edema at once.
And that's because those things occur simultaneously, often together?
Yes.
Okay. I guess what I wanted to then ask around that is, how then this would relate to, okay, so question one, with like a extension to that question then, is how does that relate to then other techniques for things kind of disentanglement? And if you don't, if you didn't initially consider this as disentanglement, what was the inspiration for this, or what work sort of led you in this direction? I'm quite curious.
So, okay, so I think the entanglement for the latent space representations is a bit interesting, because I think that that's been a lot of the motivation that they've been using to get some of the newer GANs as powerful as they get. Like if you look at the new style GAN, well, style GAN 1 and 2, the main motivation that they had in the way that they designed it was to make the representations as disentangled as possible, because it meant that they could control features much more regularly, because you could have a specific direction for nose size or a specific area for hair color or something like that. And I think the problem here was that in terms of disentangling those representations, there was actually a point where I was attempting to map the latent space for these conditions. And my hope was that there could be a possibility of inverting this process and using, in sort of a mad scientist way, the generator as a classifier, in that if you could find, if the latent space mapped, if it managed to separate out your various conditions, you could potentially map a specific chest X-ray to this learned latent space representation and segment that. So say that this is cardiomegaly in a completely unsupervised fashion. And at least with this architecture, it doesn't work very well at all. The optimization process modifies a specific image, but it's still very, very entangled in the way that this network works. Future work, I definitely think, needs to look into how general techniques for improving disentanglement has an impact on that as a process, because at the moment it's not very usable. Then as to the way that this came about, it was that if you look at the techniques currently for generating multi-label images, there's not actually a whole lot on there. There's some stuff that's come out since. So the one thing that's come out is there's a paper called GAN, where the entire process is to generate pizzas with different toppings on them, which is also set up as a multi-label problem, because you can have any combination of toppings. And it's actually been very difficult for two reasons. The first that they were having with it was that that class intersectionality problem. So there may be no source examples of certain interaction features. And so it becomes very difficult to combine that in interesting ways. And it's sometimes is just incredibly difficult to force the generator to be able to produce lots of diverse examples of those some of those very rare classes. And so my thought was that if you can do it, just generate a normal generator in an unsupervised manner, it should be able to learn all of these features, and then you can just hunt for examples in its latent space through an optimization process, because you don't have to worry about constraining an already unstable training process. You can stick with a technique that is known to make it stable, and then you can build this on as an additional that lets you, with a bit of extra computation time at inference, find examples from images that are now high quality. You'll see if you look at the GAN examples or some variants of that, some of the classes come out looking absolutely horrific, because it's trying to, it sometimes can't force that interaction, whereas all the images that come out here are largely realistic looking, even if they're not the best example of that class.
Thanks. I really appreciate that answer. That was a very comprehensive answer. And also, I'm just glad to know that GAN is something that exists in the world that these people are trying to achieve. And I also appreciate that we're running a little bit late on time. It's already sort of a little late in the evening. So I'm going to have one last question, and then we can call the talk to a close. And then for those of you who would like to hang around and chat, we generally, I'll be here until the last person leaves, but we try and make it social as possible. So yeah, Brad, my last question for you there is, especially in healthcare, safety is always an issue, and GANs are rather notorious for producing sort of spurious features. I mean, if I think anyone who's ever played around with StyleGAN, or there's another popular one, this person does not exist.com, for generating faces. You can often see some very interesting artifacts. Is there a way to provide any kind of safety guarantees using these techniques so that those kind of artifacts don't appear, or are mitigated in this synthetic training data that you're creating? Because otherwise, it could affect the classifier. Just any comments around that, I'll be interested in.
So actually, that's a very interesting domain to look into. There's something I've been interested in looking into as a solution. So there's two ways you can think about solving it. The first is moving to your more disentangled latent spaces with obviously the sampling of it is then improved, because you're not going to get like random changes in your image because you've got two very distinct classes sitting right next to each other. So for example, with that local pathology sampling technique I showed, with that example, you're not going to get absolutely random conditions showing up in between, and you may be able to enlarge that radius to sample slightly more different conditions. The other method, which is also quite popular, is as a method of improving the quality of generates with at the expense of variability, is to clip the range in which you sample the latent space. So generally, the latent space is sampled from a multidimensional normal distribution. And so what tends to happen is that the generator obviously is learning a mapping from that multidimensional normal to an image. But the problem is the ends of those distributions are poorly sampled because they're much less likely to come about. So if you're sampling from very, very extreme values at any point within that latent space, the chances are is that whatever image you're going to get back has received poor training signal from the discriminator, because it's just not that likely to have come up, and so it's not as fleshed out as more well validated areas of the latent space. And so in practice, what they suggest doing is clipping the latent space to sample within, and that's another hyperparameter you can tune within a range. And it sacrifices the degree of variability in the images that you're producing, but the quality becomes far more consistent. And most images you see in research papers that look absolutely fantastic are sampled from that kind of methodology. They're not just random samplings as you may see on broader sites. And then I think you had one last question about security guarantees or guarantees of how, if it's valid or anything. I think it's very, very difficult, because obviously you can't sample the entire distribution. You can't look at every image. You can just give an overall impression of how good the images look on average. I think what you can do is you could potentially have a classifier that tries to classify the difference between images sampled at the very extremes of the latent space versus well-sampled areas. And that may give you a pseudo quality metric as a way of potentially classifying poorly formed images. Another way is potentially to attempt to only use images that exceed a threshold on a classifier. So in that case, you've only sampled images that at least have features that are going to be consistent with a specific disease, and so they're less likely to just be malformed things with absolute craziness. But I mean, it's obviously not a guarantee.
Cool, thanks. Yes, no, that addressed my questions very well. Right, so I'll say thanks again to our speaker for this evening. It's been great having you chat to us, Brad. I'm going to stop the recording now.